Hi everyone, and welcome to session 2 of the PyBaMM training workshop. In this session we're going to talk about using submodels in PyBaMM and how that enables you to do plug-and-play physics within the framework. And so the format for this session, I'm just going to give you a little bit of an overview of how submodels work in PyBaMM, and then we've got two contributors to PyBaMM. We're going to give a showcase of the submodels that I added to PyBaMM and sort of show off the kinds of things you can do in PyBaMM by adding a new submodel. So we saw in the last session the aim of PyBaMM was to provide this open source battery modelling tool that could accelerate research and let you explore new mechanisms and so on. And the feature we're going to focus on in this workshop session is the plug-and-play physics aspect of PyBaMM. So within PyBaMM there are various different models describing things like the electrolyte, the thermal behaviour, what's going on in the particles, for example, and we can bring all these different features together and sort of pick and choose which ones we want to include. And this is particularly important when we want to include degradation mechanisms, for example, and we want to try and model the interactions between these degradation mechanisms. So the way in which models are built in PyBaMM is as a collection of submodels. So we've got standard models that you see in the literature, like the Doyle-Fuller-Newman model or the single particle model, and these are built up from smaller pieces, smaller models that describe things like what's going on in the electrolyte, what's going on within the particles. And all of these submodels that make up the battery models within PyBaMM interact, and this enables coupled multi-physics models. And so one way you can use PyBaMM is to take an existing model like DFN and change one of the submodels, so sort of tweak what's going on in a particular piece of the physics, or you can create a custom model by bringing together a collection of your own submodels. So just as an example of this, we might take the single particle model, and by default in PyBaMM that's isothermal, so we've just got submodels describing what's going on within the particles, we've got something telling us about the kinetics, and then we've got, the temperature is just some fixed value. But we might want to include thermal effects within our model, so the way to do that is to swap out this isothermal submodel and replace it with perhaps a lumped thermal submodel. And now instead of having a constant temperature, I'm solving some variable for the temperature, so I've got some temperature that varies with time, and I'm solving for that, but straight away this temperature then interacts with the other submodels that make up the single particle model. So for instance, I might have temperature dependent diffusivity within the particles, and now that immediately interacts with my new temperature that's getting updated with time, or I might have temperature dependent kinetics in Butler formula. So straight away these submodels not only let you change the physics, but they also make sure that all the different physics interact appropriately. And this kind of flexible submodel structure really allows you to do this plug-and-play mechanism and lets people implement new physics really easily, and independently. So someone can come along and they say, oh, I want to add a new model for lithium plating, and we're going to see an example of this in the showcase in the second part of this session, and they can just add their submodel for lithium plating. There might be a few tweaks to get it to seamlessly interact with other submodels, but in general they don't have to touch the rest of the code base, so they just add their lithium plating submodel and straight away they can use that in any of the existing models in PyBaMM, so within SPM, DFN, or with other submodels that I might want to turn on, like temperature effects. And this means that it's very easy to add new physical mechanisms within PyBaMM, within full models, within reduced order models, and make sure that interactions are captured. So now I'm just going to quickly give you a live demo showing how to access the different submodels within PyBaMM by passing more options to the model when you create it. So if you've been following along with the previous session, we've seen that we've done everything in Jupyter Notebooks, so I'm just going to launch a new Jupyter Notebook session, and I'm going to create a new notebook, say Python 3, and the first thing I'm going to do is import PyBaMM, and I'm going to, that's because I didn't activate my virtual environment, sorry. Perils of doing everything live. Source nbin activate. So that was a test for you there. You always have to activate your virtual environment where you installed PyBaMM before you go ahead and use it. So let's do that. I'm going to create a Jupyter Notebook. And I'm going to create a new notebook. Here we go. So let's import PyBaMM. And I'm going to, first of all, just create a DFN model with all the default settings. So let's go PyBaMM.lithium-ion.dfn. And to take a look at the submodels that make up DFN, I can just do dfn.submodels. Now this returns a dictionary telling me what the submodel name is and which submodel is being used. So I can go ahead and look here and I can say, oh, in the negative particle I've got Vicky and diffusion. negative interface, I've got butler-Volmer kinetics, for example. I can look also at the submodels that make up the single particle model. So let's do SPM is PyBaMM.lithium-ion.SPM, and the SPM.submodels. Again, I get a list of submodels that make up a single particle model. So I might look at the interface here and I say, oh, now I use inverse butler-Volmer kinetics. So by default, we're using symmetric kinetics. So I can just invert butler-Volmer to get the reaction over potential that I need for the SPM. But something that might be different between the two models, as well as that, the most obvious difference, is the behaviour in the electrolyte. So let's take a look at the submodel that describes electrolyte diffusion. So I can access this like an ordinary Python dictionary. I've got a model for electrolyte diffusion in SPM, and that's constant concentration. So in SPM, I don't include any electrolyte effects. So the electrolyte concentration is just constant in time. And if I go ahead and look at the same submodel in DFN, you can see this is something called full diffusion. So here I'm solving a full reaction diffusion equation to calculate the concentration in the electrolyte. So that's sort of how you can compare different submodels, and sort of shows you how all of these submodels are collected together to make up SPM. But what you're probably more interested in is how do I change a submodel? And the easiest way to do that is by changing model options, so passing options to the model. So I'm just going to create a new Jupyter notebook. So let's just import PyBaMM, and I'm going to create a version of the DFN model that's just the standard DFN. So I'm going to call that PyBaMM.lithium-ion.DFN. I'm just going to give that a name, DFN, just because I'm going to create another model in a second and I'll differentiate them. So I'm going to create one model, DFN, and I'm going to create another DFN model where I want to include temperature effects. So I'm going to call that TDFN, and I'm going to get the name TDFN. And then now I want to somehow tell this model that I want to include a thermal submodel. So let's go over to our documentation and see how we do that. So let's go to our website, pybamm.org, and then click on Docs. That'll take us to documentation. And then I'm going to search, let's try model options. And here we go. And then the thing I'm going to look at is battery model options. So this is telling me the different options that I've got for all the battery models within PyBaMM. So let's click on that, take a look. And it says, oh, battery models is a dictionary of options to pass to the model. So I can create a dictionary of all the different options that I might have and pass that to the model, and that's going to tell the model basically which submodels it needs to select. So you see you can select things like the cell geometry, or a lithium plating, which might be reversible or irreversible. And the thing I want to include is thermal effects. So let's just scroll down this list of options and go to thermal, and I can see I've got a number of choices here. Isothermal, which is the default, and I'm going to go for a lumped thermal model. So the way to pass this to the model is say options equals, and I'm going to create a dictionary, and thermal is the name of the option. So if we go back to our thingies, we say thermal, that's the name of the option, and then the choice I'm going to make is lumped. So let's say thermal, pick a lumped model. There's that. So now I've created two models. I've got one which is just standard DFN and one which is the thermal DFN. So I can take a look at the submodels for these guys. Let's take a look at the submodels for what's going on in the negative particle in both of these. Print that one, that's just Fickian diffusion. Print this guy, Fickian diffusion as well. So we've got the same model for the particle behaviour, that's not changed. But let's go ahead and look at the model for the thermal. And now what we're going to see is that by passing an option to the model, we've changed the submodel that's selected for the thermal behaviour. So in the standard DFN it's isothermal, and now it's lumped. So let's now just compare the results of these two models. So I'm going to put these models in a list so I can compare them like we saw in the first session. So I'm going to DFN and TDFN. Okie doke. And then I'm going to choose some parameter values just to pick a set that gives us some reasonable temperature variation with the default default options. So let's go parameter values, chemistry equals PyBaMM.parameter sets chain 2020, and then I'm going to create a list to hold my solutions. I'm going to say for model in models. Let's create a simulation. I'm going to pass in my model, and because I want to use these Chen 2020 parameters, I'm also going to pass in parameter values. And then I'm going to do solve equals sim.solve, just solve for an hour. And then I'm going to add this solution to my list of solutions solves. So that's going to go ahead and solve, and then I'm going to create just a dynamic plot of my solutions. And the variables that I want to plot are the terminal voltage, volts, and I'm also going to plot the volume average cell temperature. So because we've got a lumped model, we're just solving for an average cell temperature. Kelvin, so I'll hit that. It's going to go ahead and create a plot for me. Oh, and it says error, and it says, oh, volume average cell temperature is not found. And we'll scroll down and it says, oh, best match to this. So if you mistype a variable, PyBaMM will suggest what the names are, so I should have had a dash between volume and averaged. So let's just add that in. And you can see here now, get some slight difference in the discharge curve, and we see the temperature rises in the model where we've included temperature effects. So that's a very quick overview of how you can use options to change submodels, and now we're going to have a bit of a showcase showing off some of the different submodels in PyBaMM that have been added by contributors.
Hello everyone, I'm Simon O'Kane from Imperial College London. I added the lithium plating submodels to PyBaMM and I'm going to talk a bit about them. Just like any other submodel, to load the lithium plating model, you simply pass an argument to the options dictionary when you're loading your main model, which in this case is DFN. For lithium plating, you've got three choices: none, which is the default, reversible, and irreversible. So you then load the chemistry, parameter values, and I've updated some of those. I've updated the temperature to -5 degrees Celsius. I've updated the upper voltage cutoff to 4.21 because you actually had to set it to higher than the real value for the CCCV charge to work properly. And then the lithium plating kinetic rate constant is the main parameter to vary to control the rate of lithium plating. So then the experiment is taken from a different paper, Zhongshan Ren's 2018 paper on lithium plating and stripping. And we start off by discharging to empty. And we do that for both models, the reversible and the irreversible model. Next, you define the experiments for the CCCV charge, and we're defining 5 different experiments, each with the CC part of the charge at a different rate. And then you solve model 1, which is the reversible model, for all 5 charge rates. That's in the top cell. And then in the bottom cell, you extract the variables, start with constants, then you isolate the final equilibration phase, which is what we're going to focus on here, and then extract the variables. I've not shown all of them because there are a lot of variables to extract, but you can find it all in the notebook. And now let's look at the results. So the voltage behaves in a similar manner to in the Ren paper, which is good. The deintercalation and stripping current sum to 0 at all times as required during a rest phase, so that's working properly. The plated lithium capacity is at the bottom left, and if you look even at the steady state, there is a small but finite amount of plated lithium. That's a consequence of the equations that I've chosen. That's normal. And on the bottom right is the total amount of lithium ion inside the graphite. That's not the same as the usable capacity, but in all cases it increases as you get to the steady state. Now let's try it for the irreversible case. So you do the same again, solve it for all 5 charge rates, and then isolate the equilibration phase. And now the results are very different. If you look at the top right, the current density still sums to 0 because it is a rest phase, but you never reach steady state. So lithium ions are constantly coming out of the graphite to form lithium metal on the surface. And the reason for that is, remember, in the reversible case, there is a finite amount of lithium. Well, in the irreversible case, that becomes dead lithium. But you've always got to replace it with new plated lithium, and that lithium has to come from inside the graphite. So as the amount of plated lithium constantly increases, the lithium in the graphite decreases. So perhaps not leaving the battery at 100% state of charge might reduce the rate of degradation due to lithium plating. So let's have a look at the references for a moment. But that's not all. In the next few months, I'm hoping to add partially reversible lithium plating, where some of the lithium can be recovered, but some of it can't. If you have any more questions, please email me on my Imperial address. I look forward to hearing from you.
Hello and welcome to this part of the session. In this part, we're going to showcase how to use the many particle models and submodels implemented within PyBaMM, which involves including particle size distributions. I'm Toby Kirk. So we're going to look at two different examples today. The first is going to be, it's called the many particle model, or the MPM, which is a standalone simple model, sort of an extension of the single particle model. And then, so I'm going to show you how to use that and give you like an introduction into how to change the parameters and handle the variables. And then we're going to move on to the many particle DFN, which is implementing the particle size distributions within the DFN framework. So to start off with, part one, the many particle model. It's an extension, as I said, of the single particle model, to have a continuous distribution of particles in both electrodes. So it makes a lot of the same assumptions, whereby you neglect the X variation and electrolyte dynamics and so on. So I'm not going to go into much detail there. You can find all the details on the model equations and the assumptions and so on in this reference. And so the only information we really need today is a bit on the particle size geometry of how that is implemented. So it's just that in each electrode, we assume the active particles are all spherical, and they take sizes within a given range between some minimum and maximum, and then between these values there's a particle size distribution which sort of specifies how many there are of each different size. And it's more convenient to deal with the area weighted particle size distribution. So when I say size distribution, that's the one that I refer to, and you can see all the details in the paper. Okay, so I'm going to move on. I've put the model equations within the notebook for your reference, but I'm not going to talk about them. I'm just going to go straight into how you use the model. So for start off, we're going to import PyBaMM as usual, and also matplotlib for later. Go straight ahead and make an instance of the model. So it's implemented just like any other lithium-ion model as a standalone one called the MPM. And then let's first go ahead and inspect some of the model variables. So some of the variables are now going to vary with particle size. So in particular, one of those is going to be particle concentration. So I'm going into the variable dictionary. I'm going to search for, say, X averaged negative particle. See what I get, and I've got a few results. Notably, ones that end in concentration, and then ones that end in concentration distribution. So the ones that the many particle models solve for are the concentration distribution. These are the variables that vary with particle size. The one without distribution is then just size averaged variable, and so that'll be easily compared then to other variables, to other models that don't have size distributions. So the ones we're mainly interested in are these ones. So let's go ahead and take one of these variables. So say variables, and I'm going to take, say, this one here, the dimensionless particle concentration distribution, and then I'm going to look at what its domains are. So its dimensions. Over which domains does it vary? So the first one, its primary domain, is the negative particle. So concentration varies within the particle, and then its secondary, it varies with particle size. So particle size itself is implemented as a domain or a dimension within PyBaMM. So we'll end up getting discretized, etc., just like any other dimension. And this size domain is discretized by default into a uniform mesh, which is basically means like bins of equal width. And by default, we've got 30 number of those. So if we just loop over all the default numbers of variable points in each dimension, we'll find that in the particle size direction we'll have 30 by default, but this can be changed. So now we'll go ahead and solve the NPM. So we'll set up a simulation. The model, and then solve for about 1 hour, which is for a 1C discharge, and we'll choose some output variables, and then I've just chosen some that depend on particle size. I'm going to plot then these output variables. Here, the default particle size distributions are log normals for both electrodes, and we'll see that here we've got we can see the negative particle surface concentration depending on particle size on the top left, and the same for the positive electrode. And then we've shown the actual distributions that PyBaMM has implemented, and you can see they're quite like log normal shaped. Those are just the default distributions, but you can input any distributions you like. So I'm going to show you how you do that now. The additional parameters above those needed in the single particle model are the size distribution as a function of size and the min-max radius. So I'm going to start with a parameter set here, which is the Marquis 2019 parameter set. This does not have any size distribution parameters in it. So what I'm going to do, I'm going to choose a log normal, but its mean, I'm going to set it equal to whatever value is in the parameter set. So this just extracts the single radius from the parameter set. I've assigned it to be the mean. The standard deviation I'll pick to be 0.2 times this value. It's about 20% the mean. And then the actual function, to define it as a Python function of R, I'm going to just choose a log normal, which is implemented in it as a PyBaMM function. But you could choose any function here you like, a constant function or a binormal function, or bimodal function, sorry. And then finally, the only other thing remaining is the minimum and maximum particle size. Minimum I choose as 0, and then the maximum is going to be twice the mean. In the positive electrode, I'll do the same thing, but with slightly different values. So once we define all these things, we can input them into the parameter set by defining another. This is just inputting them into the parameter dictionary with the params.update. I just don't want to type all that out. And then again, we repeat. We can redo the solve and plot, except now I'm gonna, when I'm setting up the simulation, I'm gonna input the parameter values that It'll only take a second to solve. And you can see again that now the distributions have changed slightly. This one's widened. So here they're kind of just plotted as line graphs, but perhaps it's more intuitive to plot them as a histogram, so you can really get an idea of what PyBaMM is doing. So what I can do is I can extract the particle sizes or bins that were actually used within PyBaMM. And that variable I'm looking for here, say, is the positive particle sizes. And that'll just give me a list of sizes, but I want the actual explicit data from it. So I can do that by doing this. And then I also want to extract the distribution data, so in the same way. And the first one is the area weighted particle size distribution. But then there's the other distributions which can be calculated from it that are based on number or volume weighted, and these are calculated automatically as output variables as well. And then just with a standard bar plot in PyPlot, we can show how they are actually implemented in PyBaMM. The blue one is the one that we input, and then the others are the number and volume based. As you can see, there's about 30 different bin sizes here. Okay, so that was the MPM, which is the sort of x-averaged model. But now I'm going to move on to the size distributions within the DFN, or the Doyle-Fuller-Newman model. And for here, we're going to now introduce some x variation. But we still input all the parameters in the same way. The only difference now is that it's not a separate model, it's implemented as sort of options within the DFN model. And for all the equations that are relevant here, I can refer you to this paper here. But how do we implement this model? I'm going to refer to it as the many particle DFN for short. And we pick an option. It's implemented as a particle size option. And so the default for this is single size per electrode, but now I'm going to switch this to distribution. And then I'm going to make a model which is the DFN model, and pass it these options. Okay. And then I can go ahead and solve it for a 1C discharge, just like before. The only difference here now, I'm just changing the solver to be a faster version of the Casadi solver, so it's in the fast mode, and I've passed that. This is because it's just a quite a larger model than the standard DFN, so it'll take a little while to solve, but only a couple of seconds still. And for the output variables, I'm just going to plot some similar ones to before. Here we go. As you can see now, we have a particle surface concentration here, which depends on particle size, but also on location in the electrode, and same for the positive electrode. And again, we've got the same size distributions as before. And one final example, I'm going to compare this many particle DFN to the many particle model and the DFN for a discharge and relaxation, because this really like accentuates the difference between the models. So I'll start by making a list of the models. The first is the many particle DFN, basically the same one I just made. Second is the many particle model. The last one is the DFN, the one with no size distributions. And then to do this discharge and relaxation, I'm just going to do it by defining the current itself. So this snippet of code is now just defining the current function, and then you can then go through and loop through the models and solve them, each with the same parameter values. This will take just a moment because it's solving 3 models, and it's quite a long discharge as well, or like quite a long experiment. So it's got an hour discharge and then an hour for rest. the many particle DFN has about 30 times the number of discretization points. Okay, here we go, it's done. Now I'm going to plot just the current and the terminal voltage. On the left is the current and on the right is the voltage. As you can see, during the relaxation after the discharge, the many particle models are now significantly different from the standard DFN with one particle size. And this is the subject of the paper that I referenced at the beginning.
Okay, thanks to Simon and Toby there, who've shown us the submodels that are added to PyBaMM and how you can use those. Hopefully that's given you a bit of a flavour of the kind of thing you can do in PyBaMM by adding your own submodel. So as always, there's a number of ways to get in touch if you want some support with PyBaMM. You can head over to our Slack page, where we've got a very active community who can help out. You can head over to GitHub, where you can create an issue or a discussion. And we also offer implementation sessions. So these are a one-on-one or a group session to workshop any ideas or you might have for trying to put something in PyBaMM. So please get in touch if you're interested in any of those. For more information, you can go to our website and go to our contact page on our website to get an invitation to the Slack and to get our emails and so on. You can follow us on Twitter at PyBaMM_. Please go ahead to our GitHub page and star us to show your support for the project. You can join us on Slack and you can try our examples online by going to our website and clicking on examples, and they'll run in your browser via Google Colab. So yeah, thank you very much. That brings us to the end of session 2. Hopefully we'll join you for the rest of the sessions this week. Thank you.